Okay, class relationships, interfaces, and enumerated types today. So just for the sake of the recording, the three most common relationships: dependency, in which one class uses another class; aggregation, where you have instances of another class or other classes; and inheritance. And again, we're going to chapter 9, which is after we finish chapter 7, having done already chapter 8, we're going to look at that in much more detail. So the dependency is when you rely on some other class, usually by invoking the methods. And we've seen some. If you think about it, you can think of some examples of that. Now, you want to balance between using capabilities that already exist in classes and being overly complex. So they say strike the right balance. What the heck is the right balance? Well, that's something that kind of comes with experience. So so for example, I mean, here's a nice example where the dependency is kind of on itself. And the example is the Concat method of string, which we have seen before, where the first string, if we concat it with the second string, so this is a method of string, this is another instance of string, and the concat method creates a new string, which is basically jamming the two together and returns it. Again, remember that strings are immutable. And so if we invoke the concat method, that does not change either string 1 or string 2. Sounds like a Dr. Seuss thing. Okay, so they have a nice example that called rational number. And what's nice about it is that the rational number class is a rational numbers to an infinite degree of precision. As we've already talked, floating point and even doubles have finite precision. And if we want to represent everything as rational numbers, as a ratio of two integers, that has infinite precision. In other words, the fraction 2/7, as one example, is exactly 2/7. The problem is that on a digital computer, the number 2/7 cannot be represented exactly because of finite precision. So the book has a nice example called rational number. So let's take a look at it. Again, what I've been doing is putting the book's examples in and then tweaking them a little bit because of my own stuff. And in particular, emphasizing the Java doc rather than the plain comments that they have. So, so the idea is that we're going to represent a rational number as two integers. So rather than representing as a floating point number, we're going to have the two integers, and that gives infinite precision. So the convention which they chose, which is a reasonable one, is to make sure that the numerator, if there's a sign, it's going to be on the numerator. In other words, if I have a negative fraction, that the integer that carries that is going to be the numerator. And the other convention they had, you have to think, okay, what are we going to do if we try to give a zero denominator? Divide by 0, that can be problematic. And so there are two choices. One is to throw an error and say, hey, you can't do that. And the other choice, which was made is to say, oh, if you give me a 0 denominator, I'm going to just change it to 1. Is that the right choice? In a sense, there's no ideal choice here. But the choice is between either something like that, which is reasonable, or to throw an error, say, no, you can't do that. Since we haven't talked about throwing exceptions yet, we've caught exceptions in some of the examples, but haven't really pointed them out. So the whole error throwing thing is another issue. So what I chose to do here, which is a little different than what the book has, is that, and this is an example of a kind of dependency, because the math class has a static method, which we talked about last time, called signum. And signum it's not the Greek letter sigma, it's signum, which is the sign of a value. So the signum of a number is either -1, +1, or 0. So the signum of 0 is 0. The signum of all positive numbers is +1. And the signum of all negative numbers is -1. Now the problem here is the implementation. The implementation is only for doubles and floats. So now, knowing what we have covered earlier, if I'm passing an int to a method that wants, say, a double, then what will it do? So in a way, there's a mismatch between the types, right? But because they're primitives, there are, if you remember, the rules for promotion. So if I have a method or any context that asks for a double or a float, and I give it an int, then it will promote it to a double. It's not clear which one this has. Which one will it do? I don't know. Don't care. However, the return type, though, is going to be a double or a float, depending. So that means I have to cast it to an int. So what happens is I give it an int, it promotes it to, say, a double, it returns a double, and then I cast that double to an int, knowing it can only be 0, 1, or -1. So, and I'm doing it on the denominator, which means if it's 0, if the signum is 0, meaning the denominator is 0, then I'm going to set it to 1. On the other hand, if it's 1, meaning it's positive, I just set them. And if it's negative, then what I'm going to do is I'm going to basically flip the signs here. In other words, if the denominator is negative, I'm going to set the denominator in my class to be negative of that, but then I need to flip it on the numerator. So just think through that. If I give it, if the denominator is negative, the numerator is positive, this will make the denominator positive and the numerator negative. If I give it two negatives, this will make the denominator positive and the numerator positive, which is kind of what we want. So I did this way in contrast to what the book did, just because this is, for a case like this, a switch statement makes the intent a bit more clear than a sequence of else ifs. Now, I mean, it's not that you can't read a sequence of else ifs and parse it out. But the intent is usually much clearer if I do it. Now, the problem is that I can't, unfortunately, there are languages that allow this. The switch statement does not allow for, conditions. So it would be nice if I could say case denominator greater than 0. That would be nice. I can't do that. I have to give it an int. What are the legal values in a switch statement for the case? They are ints, longs, the integer things, shorts can allow, we won't be using those, strings and enums, and that's it. Okay, so this also uses kind of a very clever thing as a helper method. Now, this is something that we have at least sort of talked about. Okay, the helper method is the greatest common denominator, and this uses something called Euclid's method. There are actually a number of different ways of implementing Euclid's method. I don't know if you've encountered that previously, but given two integers, what is their greatest common divisor? Why do we need that? Because if I have a fraction which is reducible, then I want to store it as the reduced type. That's the decision. So if I pass in, say, 6 and 8, so 6/8, then the reduced form of that would be 3/4. So how do you get to that? Well, you find the greatest common divisor of 6 and 8, which is 2. Because 6 is 2 times 3, 8 is 2 cubed, and the greatest common divisor is 2 in that case. So how do you find the greatest common divisor? Well, in this particular case, this particular algorithm basically keeps subtracting the smaller one from the larger one until they get to be equal. And then when they're equal, then that is the greatest common divisor. And so the reduce method, which again is another private helper method, says, okay, basically, if the numerator is not 0, then find the greatest common divisor and divide both numerator and denominator by that. So just let's think some numbers in. If I put 6 and 8 in, as I said before, hopefully the greatest common divisor will come up with 2. Divide the numerator 6 divided by 2, which will be 3. The denominator 8 divided by 2, that'll be 4. And so what's being stored is the 2/4. So then they have a method that says is like. So that says if, and this is a sort of a use type of thing, because now if the numerator and denominator are identical, then they're exactly alike. So now it's important to understand that I can have two different objects that have exactly the same numerator and denominator, and they will be different objects. So when we talk about collections, we're going to get into the overriding what's called the equal method and the compare to method, which we've talked about before. But short of that, if I want to say here I have two separate objects, are they representing the same value? So okay, so enough of that. Okay, so they have here are some rational things. So here's an example of, we pass 6 and 8, but then it's stored as 3/4. Now, see, even something like 3/4, which has a fractional representation of 0.75, even that is not necessarily represented exactly in the on the digital computer. So a double of 0.75 is not going to be exactly 3/4. So here we're saying, okay, we're basically testing. This is everything we've been doing in our main methods has been like a test. So Here we're saying is 3/4 the same as 1/3? No. All right, so now here we're testing the reciprocal method. The reciprocal method, what was that? That was, what the heck? That was, where's reciprocal? Okay, so reciprocal takes the given rational number that we are invoking it on and returns one where the numerator and denominator are flipped. So the reciprocal, say R1 is 3/4, the reciprocal is 4/3. So what this also tells you that it's not reducing the fractions so that the fractional part is less than 1. It's always kind of keeping the full fractional part. And then, so we add, subtract, and divide, and all of that. Okay, so that's an example of one class depending on another class as a parameter. So you saw a number of different methods. You add, multiply, reciprocal, divide, etc. And so it depended on itself. So you might want to compare. I'm going to skip past just there. Okay. And it's useful, it can be useful to just compare particularly the constructor that the book has versus the one that I modified. Which one's right? They're both okay. I wanted to show you just how it could be done another way. Okay, aggregation. Now this is another very important relationship between classes, and it's the has-a relationship, meaning that in the class you have instances of other classes that basically make up the thing. And you can think of it as, if you think of physical objects that are made up of components, you can think of these as components. And so the aggregate relies on the objects that compose it. So here they have kind of a nice example, but the UML diagram kind of is a way of describing this. So the has-a relationship is represented by this little diamond guy here. And the thing to note here is that, see here we have two of these address classes. We have two instances of those that are associated with a student class. So each student object will have two instances of the address class, and the address class basically takes all the information, or at least much of the information for a particular physical address, into one object. And so I hope you can kind of see the advantage of doing it this way, because if we wanted to store each of these pieces of information, the street address, the city, state, and zip, in the student class, and we wanted one for the home address and one for the student address, we would need, within the student, we would need 8 extra of these things. And it's not that we have to pay a penalty for those. It's that if we were to ask the student, like, what's your home address, we'd have to kind of go and fetch all of these individual things. Whereas here, if we ask the student object, what's your home address, it simply gives us one thing. See, so this aggregation is, in a sense, a closer representation of how the actual things we're modeling are organized. because, if you think about it, an address is sort of one thing. And so the student class code, well, let's start with the address. And now address this is something that we've this is very much consistent with the kind of classes that we've been writing so far. So we have 3 strings and a long. So and we instantiate one, we have to tell it what the street is, what the town is, this which is the state, and then the zip. So here, just following the book, I'm kind of using different names in the argument. As I prefer actually using the same names than using this, but that's sort of fine. But everything is basically, all it is storing these and then having a 2-string. Now, it probably would be useful to have getter methods for each of these as well. So if you wanted to do something more with these addresses, like maybe identify all the students with a given zip code, again, that could be done, but you would have to have a lot of extra code rather than just kind of using the getter for the student. Now the student, see again, here's the UML. So we have first name, last name, home address, school address, and then overriding the 2-string method. And so the advantage of these UML things is that if you look at this student UML, then we can directly take what is written here and translate that into the code. So that goes right into here, and so we don't have to do a lot of thinking once we've done the design. Yesterday we talked about design and then implementation. So the implementation just kind of flows from the design. Now that doesn't mean that everything is a piece of cake necessarily, but it means most of the big pieces are fairly straightforward. Okay, so the constructor. Now in standard UML, they won't give you the constructor. In kind of my modified, simplified version, I will often do this. So if I were giving this UML, I would add the constructor as part of the UML just to make it clear what that is. Okay, so, and we're just sort of passing in the address for the school and the home, the first and last names, and then just a 2-string, so we're not doing a whole lot of things with this, but if we look at how we use these, okay, now the disadvantage is that in this particular case, because we are using address to the student aggregates with the address class, that means that we need to create the addresses before we create the student. Okay, so what we've done is we've kind of shoved some of the work somewhere else. And that is what I call the programmer virtue of that's not my job. Okay, so it's not the student's job to create the address. You're going to give me the address. So the student says, it's not my job to create this. Somebody else has to do it. Okay, who's that somebody else? In this case, it's our main method. So we create a school address, a home address, and we create the student by passing him. And then we create a second student. And this is where the 2-string is very helpful. So we're going to print the first name, last name, the home address, and the school address for each student, and just by kind of printing them. And so we see that, okay, John Smith and Marcia Jones And notice that they have different home addresses, but they're evidently going to the same school, so they both have the same school address. Just as I remember when I was in graduate school, I had a friend she was married, and her husband's name was John Smith, and she said like they would go somewhere and check into a hotel and they say, "Was Mr. and Mrs. John Smith?" And they kind of look at him, "Oh yeah, right." Okay, so that's aggregation. And the nomenclature is not so important. So if you don't remember aggregation, that's less of a thing. Remember the has-a, though. If you remember the three shorter ones, that dependency is uses a, aggregation is has-a, so a student has an address, and inherence is a, which we will get to once we get through this chapter. Okay, this reference. Now, this is, in my opinion, one of the most poorly named things in Java. And they use the word this, and they had a choice. They could have used something else, which was better, in my opinion. They chose to use the word this because that's what C++ uses. And they wanted to make things comfortable for C++ users. However, if you see the pronoun this, what the heck is this? Now, this is one place where Python has a much better one, and actually they took theirs from a language called Objective-C, which was another object-oriented language built on C, and that word is self. So when you see the word this, think self. Okay, this is a terrible name because this, what the heck is this? Could be this, what? Self. If I say self, it's like I'm talking about me. Okay, so this is talking about self. This is talking about me. When it's inside of an object, we've already seen this in constructors or methods where I pass in an argument of the same name, and I need to distinguish it from the instance variable, and so I put this dot instance variable to distinguish it. And the reason for that is that actually under the hood, every time I reference an instance variable, it's putting a this there. That's the reference to all instance variables is the object dot variable. The reference to all instance methods is the object dot method. So if I'm inside the class and I'm invoking a method, then if I use it without any reference, and without any object, then this is implied. Now, this refers to whatever object you're talking about. So here, this is what object 1 is about. And in this one, even though it's invoking the same method because it's invoked on a different object, this refers to this object 2 in that particular case. So, and we've seen this before. So if you use the same number, the same names, which I prefer, because that makes it clear what you're doing, but raises the challenge of possibly missing. The main thing is that this dot name refers to the instance variable. In this particular case, because name is syntactically a local variable, and local variables of the same name as an instance variable will basically shadow them, is the term. You don't have to remember the word shadow, but basically, if I have a local variable of any kind, whether it's an argument or one that I've defined within the method, and it has the same name as an instance variable, then it will it will overwrite that one. So the danger here in doing this, and no decision doesn't lack a downside. The downside of this is that if I forget to put this in, so let's say for balance, I forgot this here. Java will happily, the compiler will happily let this by. However, do you see what will happen, what this does? What this will do is, this says, take the local variable that was passed in and assign it to the local variable that was passed in. But it will not, what it won't do is it will not set the instance variable of balance to what was passed in. So, and this has happened to me more times than I would like to admit, that I've forgotten this. And I'm running the program, and it's like I'm putting numbers in, or I'm putting, not always numbers, it might be a string, it might be some other object. I'm putting them in, and it's coming out null or zero or whatever. Because what will happen here is the double value of balance will be its default value of 0. So I'll put in a balance of $1 million, and I look at my account and it's 0. And I go, what the heck? I put $1 million in. Where did it go? Okay, so that's something to just be aware of. So if you are putting, and what I've learned through bad experiences, basically, is whenever I'm putting something in and it doesn't show up, then the first place I look is in the constructor where I thought it was passing it in, and I probably forgot to put this in. Either that, or sometimes when I'm writing this, sometimes I might even forget to put this in altogether. That's the other possibility. Pretty much between those two account for 99% of the cases where I'm putting information into an object and it doesn't show up. Okay, interfaces. Now here's where interfaces came up, and this is something that Java took from, well, Objective-C. Objective-C took it from somewhere else, and I forget where they took it from. But all languages that exist today have mostly stolen features from some other language. So it's like, that's the way of the world. Sort of, you see, I'm a Mac user, so I like Macs, but I'm not like religious about it. So, Mac users were saying, well, Windows kind of stole the whole mouse and user interface thing from Apple, right? More or less true. Of course, Apple stole it from Smalltalk. And Smalltalk.
I know the thing. There was always a mouse associated with any kind of software program that I've always used. So I guess you were around that.
Yeah. Oh yeah. There was a time when Macs first came out, they were derided by DOS users. Okay, now DOS was, if you ever used the command prompt, that used to be the whole thing, the whole computer. That's what you got. When you fired up your computer, you got one big screen of a command prompt. And you could type some stuff in. And they had a lot of business applications, Whereas Mac was kind of, they had graphic application, we could kind of draw and do stuff, and that was really, kind of toy stuff. That was for kids, according to the DOS users, because real men used the command line. And then at some point they realized, we can do, this Apple thing is really pretty cool. So they basically kind of stole some ideas from it, but Apple had stolen theirs from somewhere else. Basically, the story on that is that Steve Jobs visited Xerox had this development lab called Park Place. It was up in Palo Alto. Had a lot of ex-Stanford students. That's where Smalltalk came from. That's where the mouse came from. That's where object-oriented programming came from. And Steve Jobs visited them. He saw the mouse. He saw the object-oriented stuff. And he thought, well, these two are pretty cool, but I'm gonna do the mouse thing. And that's kind of his first thing. The early Apple, the Apple II, ran with a cassette thing. And you needed a TV to use the monitor because it was a real mess. But back in the old days, you kids have it so easy.
I use the command prompt now, and I hate my life whenever I have to use it.
Yeah. So yeah, but that used to be all you got. So anyway, the point I'm trying to make is that there's nothing wrong with stealing. Stealing is good in this case. All right. Within limits. In this context, so if you yes, yeah. Okay, so what Java interfaces were solving is a problem that arose when you had something called multiple inheritance, which we'll talk about how Java does inheritance. But it turns out that in many cases you want to specify how you're going to interact with the objects without saying exactly how. In other words, you want as much as possible for the methods and the objects you're interacting with to be a black box. You don't know what the heck is going on inside. And that's something that we do all the time.
I love that.
Yeah. So now, as the developer, you're the one who needs to make what's in the black boxes. But as a user, it's like it's the principle again of ignorance and apathy. So you don't know, you don't care. All you know is that when you invoke particular methods, you expect certain results, and how it does it, you don't really care. So, just as an example, we were looking at this rational number thing. I talked about how there's a method called GCD, which gives the greatest common divisor of two numbers. And I said this is close to Euclid's original one, although from what I understand, Euclid probably didn't invent this, but he got his name on it. Just that's the way things are. But there are many different implementations of this. For example, using a sequence of modulo arithmetic is another possibility. And if you are a user of this method, though, you don't know or care exactly how it does it. All you care is does it give you the right results? And so which algorithm does it use? Well, you might care about performance. How does this perform compared to other ways of doing that? But again, as a black box user, all you care about is that performance. So if you don't like this one, then you can maybe find another one. So the idea there is that this GCD with two ints as its argument is like an interface. So the interface says, when I call GCD and I give it two numbers, it's going to give me the greatest common divisor. How it does it, I don't know, and I don't care. Okay, so that concept is what the interface is about. And we'll have to pick that up again on Monday.